In the last class, we have studied about the nomenclature of alkyl halides. Today, we are going to discuss about nature of carbon halogen bond in alkyl halides. So, this is what a general alkyl halide is represented. We know that a halogen is more electronegative than carbon, so that these bonded pair of electrons always tend to move towards the halogen atom, and hence the halogen gets partial negative charge and carbon gets partial positive charge, so that we can say the carbon halogen bond in an alkyl halide is a polar bond. We can say a polar bond. Why it is polar bond means due to electronegativity difference between carbon and halogen. So this is nature of carbon halogen bond. Then isomerism in case of monohalogen compounds. Monohalogen compounds. So we all know that an isomerism is basically of two types. One is a structural isomerism and the other is stereoisomerism. So in structural isomerism, we'll come across 5 types of isomerisms: chain isomerism, position isomerism, functional isomerism, metamerism, and tautomerism. Among those structural isomerisms, these monohalogen compounds exhibit chain and position isomerism. So what is a chain isomerism? A chain isomerism arises due to change in the number of carbon atoms in the parent chain. For example, if I take this compound in this formula, the parent chain consists of 4 carbon atoms and hence its name is 1-chlorobutane. 1-chlorobutane. Similarly, in the next case, its formula is also same. Molecular formula is same. Usually, chain isomerism is nothing but 2 or more compounds having same molecular formula but differ in structural formula. So they differ in the structural formula. So these two possess same molecular formula, but these two differ in the number of carbon atoms in the parent chain. Here it is 4, whereas here it is 3. So these two are chain isomers. And position isomerism. It arises due to change in the position of substituent or any functional group. Now halogen is our substituent. So in these examples, these two possess same molecular formula, but the position of substituent. In this example, it is at first carbon. In this example, it is at second carbon. So 1-chlorobutane, 2-chlorobutane. Hence these two are position isomers. And then the next one is this optical isomerism. So it comes under stereoisomerism. So in the next classes, we'll discuss detailedly about this optical isomerism. Now I will give you a simple information about this optical isomerism. Optical isomerism is nothing but it arises due to change in the rotation of plane polarized light. Rotation of plane polarized light. If any substance rotates a plane polarized light towards any direction, then that is said to be optically active. One of the condition, see, we have so many conditions to exhibit optical isomerism. One of the condition to exhibit optical isomerism is presence of an asymmetric carbon atom. So what is this asymmetric carbon atom? So asymmetric carbon is a carbon which is bonded to four different substituent atoms or groups. So this is an example. Now this carbon, it is bonded to hydrogen, CH3, chlorine and ethyl, C2H5. So all these four are different atoms or groups. So this carbon is said to be asymmetric carbon atom. So any molecule to exhibit optical isomerism, one of the important conditions, this is not the only condition, one of the condition is presence of asymmetric carbon atom. So this is about the isomerism exhibited by monohalogen compounds. One is chain isomerism, the second one is position isomerism, and the third one is optical isomerism.